Hi, in this last class I discussed the behavior of second order linear systems. We saw how poles affect the behavior of your system. So in today's class we'll discuss two additional tools that are quite commonly used in context to controls. Those are transfer functions and state space representations of such systems, and we'll see how these tools can be used to understand the behavior of your system in hand. Okay, so let us start. So let us look at the transfer function representation first. So the transfer function Hs is a linear mapping of the Laplace transform of the input, that is Xs, to the Laplace transform of the output, that is Ys. So Ys is Laplace transform of y, that is function of time. Similarly, Xs is the input, Laplace transform function of xt. Okay, so the transfer function is defined as Ys by Xs, that is the output Laplace to the input Laplace function. Okay, so this term is quite often used extensively for referring to linear time invariant system, that is LTI systems. Linear system, but they are time invariant. Time invariant means the properties of the system doesn't change. Let us say you have a system like a spring mass damper system only. So if it is Fmx double dot Bx dot plus Kx, so M, that is the mass, damping ratio, and the stiffness of the spring doesn't change with time. So that is what the characteristics of that system should not change with time. So those are linear time invariant systems. Okay, so using this, input and output can be represented like a block. So you have a transfer function that goes here, this is your output and this is your input. So this type of block diagram representations are very commonly used to represent your control architecture also. Let us say if it is a simple PID control or any sort of control, so you can represent each of the blocks with having one transfer function within. Okay, let us say you have a closed loop system. So here goes your input, you have a comparator, so you have a controller over here. This can be a PID controller. This gives an output to the robot. Robot gives you an output, and finally that output is sensed. Then you have a feedback line that comes here and goes here. So this is your comparator. So you can have a signal that comes here, that is the desired input. This is the output which is sensed. So you have a transfer function which is over here. Okay, that is the feedback transfer function. And similarly you have a controller transfer function that comes here, and this is your robot transfer function. So every stage has got an input and an output. Okay, and each block represents one transfer function. Okay, so this is a very common tool which is used to represent the whole of the system sometimes, not just a control system. It can be just open loop system also. So your system itself can be represented like this, and overall your system may have a system transfer function which looks very much like this. Okay, and over here in this transfer function you have numerator, you have denominator just like this, and maybe you have this can state the behavior of your system also. We'll see how it can do that. Okay, so yes, let us start with a simple system, spring mass damper system. We have used this quite often now because this represents very analogous to our own control system that we are looking for, that is the robot control system. That also is a second order system, but that is not that linear. So it can be linearized to say almost near to this. Okay, so that is the reason I am using this quite often. So yes, most of the mechanical systems should be very near to this. Okay, if not exactly this. And there are terms which are analogous to M, B and K which are put here. So that is the reason this is quite commonly used. And yes, the taking Laplace on both the sides, you have seen with initial condition, if they are 0, that is x0 is 0 and x dot 0 is 0. That means initial position and velocity is at 0. So if you take Laplace, so what you should get, it is Laplace of ft is fs. Similarly, m is a constant, so Laplace of x double dot t is s square xs, and x dot t, if you take Laplace, it becomes s xs. So every time you take Laplace, there is a term that comes here which says it has x0, okay, at the end, or x dot 0 at the end. So because those terms are 0, you are just remaining with xss over here. Similarly, k times of xt will become, k being constant, it will go here, and you have xs that comes here. So taking xs common in whole of this expression, so x can be taken out, so you can see a relation which is very much like this. So if you take their ratio, it gives you gs, that is the transfer function. So it says 1 by ms square plus bs plus k. So this is the open loop transfer function of spring mass damper system, where output xs and the input is related by this. So your block would say something like this. So you have 1 by ms square plus bs plus k. So you have input that comes here, that is the fs, and you have output that goes here, that is xs. So output by input will give you the transfer function, that is gs, which is here. Okay, so this is what is meant by transfer function. Okay, let us see how this represents the behavior of your system. You can clearly see you have something in the denominator. You are very much familiar with this already. So this was what? This was your characteristics equation of your spring mass damper system, and the roots of this we use to analyze the behavior of your system. Okay, so yes, so this can alternately be put like this. So we are not very much concerned in this formula now, but yes, this also includes the terms which are very much the same, only the constants will differ. So it is s square and s over here and the denominator. So this also gives you a similar characteristics equation, and this will also take you to the same place. So yes, there are two poles that are S1 and 2, that is given by this. You have already seen that, and discriminant over here basically will tell how is your roots. Roots are real and imaginary, so both the parts are there, or it is purely real or it is purely imaginary, or roots are equal, or it can be just 0. So it all depends how is your roots, and that will govern your system behavior also. So roots can also be expressed like this. Okay, so yes, the poles are nothing but the roots of the characteristics equation formed by equating the denominator to 0. So this is your denominator. To take the roots of that, so that is known as the poles. Okay, so equating the numerator to 0, that is zeros. Okay, so the roots of the numerator are known as zeros. Okay, and poles and zeros, they affect the peaks and the amplitude of forced and natural response of these systems. Okay, so this is how a simple spring mass damper system is, and this is your transfer function, and the denominator over here is the characteristics equation, and roots of this basically govern how your system is going to behave naturally, as well as by acted upon by, if it is acted upon by any external force. So you have seen the behavior already, okay, using this, so need not to discuss much. So idea is to come out with the transfer function of your spring mass damper system. So that is what is observed here. Using MATLAB code also you can analyze your system by simply expressing your system like a transfer function. So you know now you have a transfer function with numerator as 1 and denominator simply is the polynomial definition that goes at the denominator. So in case of the system that we have already seen, it has 1, 5 and 6. So you see it is ms square plus 5s plus 6. So you can just see it is b square minus 4mk. So okay, so m here is 1, so it is b square, that is 25 minus 4 into m into 1, that is 24, so it is 1. So you see you have a discriminant of this, that is telling it is greater than 0. So you have two roots, both are unequal, they are real also. So that is an overdamped system. So you have seen the behavior already. So that is put here in the denominator. The second system is 1 1 1, that is s square plus s plus 1. And the third one is the one that we have already analyzed all these three. So it is 1 4 4. So we already know how the behavior should come out to be. So I am defining my system transfer function as numerator and denominator. MATLAB allows you defining it in this way. TF is the function that I am using here. So yes, these are my system, that is system 1, system 2 and system 3 with different denominators over here with the same numerator that goes here. And I have observed the step input behavior of these systems. So for the step input, system 1 and 2 and 3 are plotted here. Okay, so this is just a label. So they are plotted here. So let me just see, it is something like this. So you have system with real and unequal roots. So that is coming here. This is an overdamped system. And next one is real and unequal roots. Real and equal root, that is your critically damped system that comes here. And then you have complex roots. So roots are imaginary. All the roots are in the left half of your complex plane. So you have already seen that. So this is your behavior for that. Okay, so this is how it comes. Okay, so this is what is transfer function, and that can be used to analyze the behavior of your system. Okay, so based on the input and time that goes from 0 to 12 seconds over here. So this is the behavior you see. And same can be studied even using MATLAB Simulink, that is a symbolic tool that MATLAB has. So it supports block diagram based approach for programming. So you have a step input which is fed to the block with transfer function defined like this is the first system, this is the second system, this is your third system. So all of these you already have done it. So this is real and unequal root, this is complex root, and this is real and equal root. So you see similar kind of plots can be observed by using a scope which has 3 inputs. So you see you can observe it. So each and every time instant you can check the values by sliding this. So this shows you the values. So at this moment, what are the values of all the plots? So yes, this is an additional tool which is supported in MATLAB to check the values. Okay, so this is how it can be done. Okay, before we move further to state space representation, let me just familiarize you to ordinary differential equation and the kind of thing we are going to use it for. So let us just discuss this. So an ordinary differential equation contains one or more derivatives of a dependent variable, that is y, with respect to a single independent variable, usually time in case of physics based system like ours, like robot. Okay, so yes, so this is how it is defined. So your system normally should look like this. Okay, so that is pth order derivative of y, which is here. So that is equal to, it is equal to function of time and y1, y2, y3 and yp. What are those? So they are basically derivatives of y. Okay, so higher order differential equation of pth order can now be represented as p first order differential equations. There is reason for it, why we are converting this higher order differential equation to a set of first order differential equation. If it is highest order is yp, that is pth order, so you have p first order differential equations will be formed. So yes, the p first order differential equations are, they look like this. So it is these are different variables now. Okay, and these are derivatives of y. This is no derivative, this is first derivative, and p minus 1 derivative. So y1 is equal to y, y2 is equal to y dash. Similarly, there should be y3 is equal to y double dash, and so on and so forth till yp is equal to yp minus 1th derivative. If you substitute this to your original differential equation, this results in a system of p first order equations split. If you split them all, you should get something like this. So y1 dash is equal to y2. So it is just this one that is put here. Similarly, y2 dash is equal to y3. So that was your second term. So y3 is nothing but that will come here. Y3 should be equal to y double dash, and y double dash means that is y2 dash, that can be obtained from here. So that comes here. Similarly, y3 dash will be equal to y4, and so on and so forth till finally you will get yp dash. So you should get your original function which was here. So this is your ordinary differential equation. Okay, that comes here. So this is how you can split your system to a set of systems. Okay, so that means you have first order equations that represents independent variables. So those can be substituted and they can be finally put like this. Okay, why this is done? Because this representation is quite useful for obtaining numerical solution of differential equations using the well-developed first order equation solvers. So MATLAB has already a set of ODE solvers, ODE 4.5, ODE 5, ODE 4. Those are nothing but Ragakuta solvers, and many other types are already defined. Okay, so that is nothing but they are solvers for first order differential equation. Solver for first order differential equation. So in order to solve kind of equation which is like this, so you have converted it to a set of first order equations. So now you can club them all together and use ODE solvers to solve them. So this is the beauty of having expressed your system to a set of equations which are like this. Okay, so ODE is solved by starting from an initial state, that is what are the states at initial condition, that is the boundary condition, and it sets the period over which you have to get the solution. Okay, and at each step the solver iteratively applies the ODE solver algorithm to the results of the previous step. So it iterates from the initial step to next to next to next, and finally it gives you a vector of time steps, that is t is equal to c, t0, t1, t2, t3, and at each of these time step you get also the value of y. So that is y0, y1, y2, y3, y4, y5, and so on so forth till all the values of y. So all the y's that you saw in the previous slide, so that is obtained at every time step. That means you have got all the variables, all the derivatives of y. So that is what is obtained. So if it is acceleration, you get velocity, you get the position at every instant of time for any system like a spring mass damper system also. Okay, so yes, number of coupled ordinary differential equations can be specified and can be solved simultaneously in MATLAB like this. So they can be packed like this. These are the independent functions, okay, of t and the derivatives of y that goes here. So they are all different functions. They are all coupled ODE equations which has same input variables and one output variable. So not basically the input and output variable, basically these are the derivatives. Okay, got it? So this is how it can be expressed. So this is all set of first order equation. Okay, so now just take one example of ODE and see how we can convert it to a set of first order equation. Let us say you have a system which is like this. It is a third order equation. So d cube y by dt cube. So it is with respect to time d square y by dt square, and you have y plus 1. So the system can be represented like this in compact manner. So prime here, y single prime is basically dy by dt, double prime is d square y by dt, and y triple prime is equal to d cube y by dt cube. Okay, so this is how they are. So now I'll just use the substitutions for y, y prime and y double prime. So all the derivatives, I have this substitution. So y1, y2 and y3, I'll put them to the original equation that is here, and I can get to this. So this results in a set of first order equations. So if it is third order, you see you got how many equations? 3. So number of independent first order equations will be depending on the order of your original differential equation of the system. So if it is 3, so you got 3 over here. So each one of them are first order equations. They can be packed together and put to ODE solver, and you can get the solution of that. So we'll stop ODE discussion over here and we'll move further with our system again. So let us come back to state space representation. So any dynamical system are typically represented using a set of n second order differential equations. So if it is of second order differential equation, so number of first order differential equation that can be formed out of each one of them, okay, it should be 2. Okay, so if it is n, it is 2n. So its state space is represented using 2n first order differential equations. Okay, so the set of 2n differential equations representing the dynamics of a multiple input multi output system can be represented in a compact manner. So this is what is your state space form. Okay, so multiple set of equations you had for multiple input and multiple output system. Okay, and there were 2n differential equations, first order equations, that represents your dynamical system. So each one of them can be clubbed together in compact manner like this. Okay, so what are these terms? A, B, C and D. So the matrix A is a 2n cross 2n state matrix. B is the 2n cross R input matrix. Okay, C is M by 2n output matrix. D is the M cross R direct transmission matrix. So each one of them has got some significance. We'll see by example. Okay, so let us come back to our old friend, that is spring mass damper once again. So dynamic equation of motion this time is same. So that is F is equal to mx double dot bx dot plus kx. Now I want to express this as a state space representation. So what should I do? So yes, I'll assume the substitution which are like this. So that is x1 is equal to x and x2 is equal to x dot. So what effectively I am doing, so first one is x1 dot is equal to, so what it should tell me, so if it is x1 dot, so it is x dot, so it is x2. Got it? So from these two you can quickly obtain this. Now x double dot is equal to minus k x minus b x dot, right, minus f. So it was just m which has multiplied here, so you can write it as m, m and m. Got it? So it should be plus over here. So yes, so now you substitute these again here. So when it is x, you can say it is x1. So you write x1 here. If it is x dot, you can quickly write x2 over here, right? And this remains as a constant. So ultimately x double dot here is basically x2 dot, because you see x dot is x2, so x double dot is x2 dot. Got it? So that is what comes here. So you can write x2 and x1 dots. Okay. So these are the derivatives. Okay. Now the output part. So y is equal to x1. So that is very trivial. So there is nothing called d over here. That turns out to be 0 in this case. So that was your output equation. Okay, so equation 3, this one can now be written as 2 and 3, both of them together in compact manner. So I have put these two over here, and again if you see, I have taken x1 and x2 directly over here. So that is appearing as x1 and x2 both are here. So that comes in the next column. So it is minus k by m, that is transferred here. Similarly, minus b by m from the equation 3 comes here, and it has both the terms for x1 and x2. Whereas in the first one, it is only x2 with no coefficient, just 1. So it is 0 and 1 over here. Now the part which is here. So f appears only in the second, that is x2 dot. So this turns out to be 0. So it is expressed like this. And y has got just x1 term. So it can be written as this. 1 multiplied by x1 and 0 multiplied by x2. So it is nothing but a simple straight equation. So that comes here. So this is your input and output relation. So those are where the state space forms now. So now comparing this, you can write simply this one is your x dot, this term is your a, this is your x, again this becomes your b matrix, and you have u, that is the input, that is f, u, that comes here. So exactly f is your u. Got it? So x is 2 cross 1 state vector, a is your 2 cross 2 state matrix, b and c are 2 cross 1 input and output matrices. Okay, the output now is a direct transmission term with d is equal to 0. Okay, so that is scalar because you have no d term over here. Okay, so there is no direct transmission which is happening. So y is just this. Okay, so that is c times of x. If it is bold C capital, it is this. So this is equivalent to C transpose, the way it is written here. So it is like transpose, so it is this small c transpose. So both are same. So this is how it is converted to state space form. Got it? So yes, now using this also we can analyze my system. Okay. So let us just see if a spring mass damper in state space representation, I am using MATLAB now to see its behavior for step input. So how is it defined in MATLAB? So your system, let us say it is your m is equal to 1, b is equal to 5, k is equal to 6. It's a overdamped system. For time variation from 0 to 10 seconds, I want to do that. So A matrix, I have just put it exactly as it is appearing here. So I have defined my matrix A, B and C over here and created a state space system of equations, stored it here in sys. So A, B, C and D comes here. So step input to this system with time t variation 0 to 10 at a step of 0.05 seconds. So it is plotted. So it gives me a similar behavior the way it should be. Right? The way we have seen earlier in our previous analysis. Okay. So this is how state space can now be used to see the behavior of your system. So how this is all done in the background, basically the transfer function from state space is obtained using, for this single input and single output system, it has just one input, that is force, and output is displacement. So for them this becomes quite trivial. So can we do that as well? So let us just see if it is possible. So how was your system? I'll just show you once again over here. Yes, so this is your state space equation. X dot is equal to AX plus BU, Y is equal to CX plus DU, input and output relation. So taking Laplace of both of these which are here. So yes, let me do that here also. So it is X dot is equal to AX plus BU. So taking Laplace should give me S of XS and A times of XS plus B U S. B is the matrix and U is in Laplace. Okay, so that will appear here. Similarly, if you convert Y now, so Y was CX plus DU. So if you take Laplace, you should get YS is equal to, instead of C, I know it is, both were equivalent, so those constants are put here. It is XS here plus DUS. If at all D is absent, this term goes off. Got it? So this is how it can be written as. So just by taking the Laplace, these two equations are put. Now you just take out XS from this equation, that is equation number 6, and substitute it here in this one. What do you get? You get YS is equal to C transpose S. I is a compatible unit matrix. So if it is second order, it is diagonal elements are 1, rest are all 0. So it is unit matrix minus A whole inverse B plus DUS. Correct? So it becomes exactly this. You can try doing it yourself. So you can just take out XS from here, substitute it here, you will get to this. Okay, so now you can relate your output and the input. So output was YS, input is your US, so that is your transfer function. So that is given as this. So this is your output, this is your input, so this becomes your transfer function. So what it is here basically, if you can write inverse, if you put inverse over here, so what it is, SI minus A transpose by determinant of SI minus A. So if you convert it, you will get some polynomial in S, and the numerator and the denominator will have the determinant of SI minus A. So this gives your transfer function. So this is having the numerator with polynomial in S, denominator as SI minus A is this one. Okay, so now the denominator is the characteristics polynomial of GS. You already know that. So denominator of the GS should give you the characteristics equation of this system. So the roots of this determinant should tell me the behavior of the system as well. Okay, so the eigen values of A are identical to the poles of GS. You see, if I equate this also to 0, so that means I am finding out the eigen values, and same was for finding out the roots also. They are identical. Okay, so taking inverse Laplace of GS, so that is input and output relation. If you take the inverse Laplace of this, so you should get the time domain equation of the system, and again this can be expressed in the state space form. So if you know the time domain equation, you can convert it to the differential equation and you can express them by proper substitution to state space form. So both ways you can do. You can do transfer function from state space representation, or you can do otherwise also, right? So both are equally helpful. So at least in SISO system it goes like this. So let us again see our own system. How was ours? So let me just show you once again our original slide. So this was the system, state space representation of your spring mass damper. You see what was your A? It is matrix that is shown here. Got it? So it is exactly this one. That is your matrix A. This is your B matrix, and then you have C transpose, that is C matrix, and output matrix and input matrix, they look like this. So copying that from here, I can now put all those values to this. So SI is, because I know it was a second order system, I is compatible, so it is diagonal elements 1, so it is Si minus A. So this is A that comes here. So if I do that, I'll get to this. So again, taking inverse is very trivial. So you just take inverse. What you will get? You get something like this in the denominator. That is nothing but the determinant of this matrix. Got it? So that is coming here, and whole of the transpose that comes here. Okay, so transpose by determinant of this. So determinant is very trivial, so you can just find it out. Now I can extend it further. I can use this to write the transfer function. So GS is my transfer function. All the values I have put from my previous slide. So that was here. Okay, so A, B, C, all the values comes here. So A, you have B and C that goes here. D also is here. D is equal to 0. That comes here. So this is your B. This is exactly Si minus A inverse. So that comes here. And C transpose is here. Got it? So this gives me 1 by ms square plus bs plus k. We have earlier seen also exactly this should be your transfer function when you just took the Laplace of your given system. So I got to the same result, and again this is my characteristics equation. So this is what was expected also. So roots of this will tell the behavior of my spring mass damper system. So I can analyze it anyway now. So let us see if MATLAB allows me doing so. So yes, conversion from state space to the transfer function is also possible in MATLAB. So your system goes here, M, B, K, and your input. Okay, so that is here A matrix, B, C matrix you can define. You can extract it directly from your earlier slide. A, B, and C matrices. Okay, all those are available here. Okay, so you have simply put it here, and now state space to transfer function. So straight away you can get the numerator and the denominator. Running this gave me this. Okay, so yes, this was your numerator and this is your denominator. What this says, it is coefficients basically. These are coefficients. You see this is M, B and K. 1 by ms square plus bs plus k. So coefficient of s square, that is m that comes here, b and k. So that is all here. So this is what can be directly obtained. So MATLAB also allows you to convert state space to a transfer function format. Okay, so again let us analyze a simple robot-like single off planar arm. Okay, if there is no torque, it becomes a pendulum, and mind it, it is just a planar pendulum. It is not a conical pendulum which has 2 degrees of freedom over here. It is just one off. Okay, one cylindrical joint that comes here. It can go like this. Okay, so it has a solid link with mass m. So mg force that comes here. Mg sine theta, you know, that is the driving force with L by 2 distance, that is at the center of mass it is acting. So it is giving you a torque which is given by mg sine theta into L by 2. Okay, so this is the driving torque basically. Okay, so you see this was your original state space form. Okay, so this is what we want to obtain now. So dynamic equation of motion of this planar arm will be given as tau minus, this is the external torque, this is the torque which is acted due to the gravity. So difference of that is actually the driving torque. So it is nothing but I theta double dot. I is moment of inertia of this link. Okay, so that is 1 by 3 ml square. Theta double dot is the acceleration at an instant of time t. So the same equation can now be written as this. What is theta double dot is equal to 3 tau by ml square minus 3g by 2l sine theta. So theta double dot. So yes, now I can use these substitutions. So x1 is equal to theta, x2 is equal to theta dot. So this is the first one that you know it is very trivial. So x1 dot is basically theta dot. So that is equal to x2. This is the first one. Now the second one, theta double dot. theta double dot is x2 dot, so that comes here, so that is x2 dot, and that is equal to 3 tau by ml square minus 3g by 12 sine theta. So instead of theta I can write x1, so that is coming here. Okay, for very small oscillation, because you see this is a non-linear type of system, so it cannot be directly converted like a state space form. So this time you have to do little linearization. So for for very small oscillation, sine x1 tends to x1, so very near to that if you are making a small oscillations. So this approximation can be done. So I can directly put, instead of sine x1 I can put x1. So my new system, as there is no input torque T, u becomes equal to 0, and the output relation can be written as y is equal to x1. So putting them all together here, so it is this. So it is x1 dot x2 dot, that comes here, and extracting the terms now. So this is your a, this is your a, that comes here, ax, x dot is equal to ax plus bu. So this is your b and u, that is the tau, which is the external torque which is acting. So, and again output is y is equal to c x, this is your x, and du, d and u. So u is again the input and there is no d. Got it? So this is how you have converted your single degree of freedom planar arm dynamic equation of motion to state space form. Now it is integrable, it can be analyzed, you can do anything with that. Let us do that. So now I'll analyze my, that is a step input response, okay, to this wound off arm with 0 input torque. So now I have defined my A, B as we have obtained earlier in this. Okay, exactly, I'll put this as A. I know the values here, m is equal to 1, length of the link is also 1 unit, and g is 9.8 meter per second square, L is 1 meter, m is 1 kg. Okay, so I have defined whole of this here as we have obtained just previous slide. So I'll put those values here and I have got the matrices now. So I have now state space using SS function. I have defined my SS function in sys. So that is A matrix, B matrix, C and D goes here, and step input is given and analyzed with time. Okay, so this gives me a plot which is SHM. You see, it is simple harmonic motion. For a small oscillation it behaves just like a pendulum. Got it? So this is your system, and this is what is expected, because you are not acted upon by any external force and there is no joint damping. That means it will keep oscillating forever. Okay, so that is what is shown here as a result also. Okay, so that's all for today, and in the next class we'll discuss a robot joint, a DC motor model. So we'll go very near to what we are actually intending for. So we will now start doing the joint model of a robot using a DC motor model. Okay, so that's all for today. Thanks a lot.